My name is Dick Taylor. I'm the director of the Institute for Software Research, and it is my pleasure to welcome you to the first Distinguished Speaker lecture of the year. And it's also the last day of the quarter. It's the day for visiting prospective PhD students. It's the last week of classes before spring break. It's a good day. It's also great weather. So, my pleasure to introduce Professor Arie van Deursen from Delft University of Technology. Excuse me. As I said, this is the first of 4 lectures this year. So with that, I'm going to let Arie go ahead and start.
Okay, ladies and gentlemen, my name is Arie van Deursen, and I'm very excited to have been invited here. I spent today and yesterday talking to many of the people here, and this was very inspirational. I learned a lot about many different things, and I'm very excited about all the wonderful things that are happening here. When I got invited, I knew Irvan a bit, and what I knew of Irvan was software architecture. That is the thing that is happening there. So I learned today and yesterday that a lot more is happening, but software architecture is one of the big things here. So I thought, well, what I should do is take my own software architecture research and present it here to get some feedback from the real experts. So I'm really looking forward to your feedback and to your discussions on that. And software architecture, in my case, the recent work, it's really about evolvability. So architecture is about the big structures, but in order to deal with evolvability, and the particular angle that we're going to take is metrics, so measuring to what extent your architecture can deal with change, because change is the fundamental thing in software engineering. The work that I'm presenting is actually a joint work with a couple of people, in particular with Erik Bouwers. He is the PhD student who did most of the work what I'm presenting today, and Joost Visser, who is head of research at a company called SIG, and I'll talk a bit more about this company later on. So that's the context. Before I start, what I'd like to do is give a bit of context about myself and the place where I come from, which is Delft. And here you can see Delft. It's painted by Johannes Vermeer, which you may know from the girl with the golden earring. This was painted in 1662. And actually this view, it's still like it used to, like it's now. So this is the new church from the 14th century. And this is the old church from the 13th century. And when I walk from the station, which is over here, to the university, which is over there, I still walk along this exact canal. And then there's a boat with all Americans who are going to do some touristing. And there are 2 ladies, and I can say hello. So in a way, not much has changed. But if you go a little to the left to the station, the view is like this at the moment. So what's happening is that there are tracks through the city right now, and they are going to move them downwards in a tunnel. So they're digging a big tunnel here, and that's where the trains are coming. So big change. But you can still see the same new church, still called the new church, and the old church. So this is the tunnel project at the moment, and it's a 2-mile tunnel they're working on, including a station. It will look like this, with traditional Delft blue tiles in the station, so quite nice. 4 train tracks underground. There will be trains every 10 minutes, I think. Parking for 100 cars. And it creates a lot of space above the ground. So we have 1,200 new apartments, a big park, and parking space for 4,000 bikes, which will be full all the time, so you have to search for the place to park your bike. So why am I telling this? Well, this perspective that we'll take today is that of a project manager. So think of yourself as managing the creation of this project. So a 15-year project, 650 million euro, that's like 800 or 900 million dollar, I think. And you are the guy responsible for all this, or you are responsible for this. What are you going to do? Well, hopefully everything is going all right, but you have to report progress to your manager, to the minister, and how do you deal with all that? So that's the perspective that we're going to take today, managing a big project like this. And then turn that into a software project. So we're not talking about tunnels today, but about software. Then you might think, 650 million euro. Well, there are no projects, software projects like that, are there? Well, there are plenty of those, and many of them actually fail. So there's the Dutch police, for instance, has software. Initial project failed, around 100 million wasted, and now they're redoing it, and that's another 300 million. So that's 400 million just to automate the police IT. So this is actually what's happening in IT, and well, perhaps it's not 15 years, but the software will run for a long time. It will continue to change. So we're talking similar timescales, similar money in software engineering as well. So we have to deal with that. So that's the perspective today. Okay? By the way, if anyone has any questions, just ask, and I'm happy to answer. So that's the Delft situation. Then my university and my group, it's called the Software Engineering Research Group, organized a little differently than here. But in our group there are various professors, various PhD students, and various postdocs working on a range of different topics. Mostly I work on software testing, but today I'm not even going to say the word testing again. So this is not a testing talk. Software architecture is what I'm going to talk about today. Repository mining, that's learning from the history of software development as it is stored in revision systems. So today we'll actually be using that in order to look at metrics and how metrics would behave in the past, and then we can learn from that in order to apply it in the future. Collaboration, what I learned in the last 2 days is that the role of the people is very important, the personal perspective is very important here in Irvine, and we are also interested in that, in the collaboration aspect in Delft. And actually what I'm going to talk about today, it is about metrics, it's about architecture, but it's also about people using architecture and people using metrics. So some of the lessons that I learned from the collaboration research, I put it in the metrics research today. So there's a nice connection there. And the other 3 topics are nice and cool, but I want to touch on them today. So when we do research in Delft, we quite often do it together with, well, it's software engineering, so we want to do it together with practice. So we work with various companies. Here are some of the companies that we actually work with. Today I'm going to talk mostly about our work that we do with this particular company. It's the Software Improvement Group. It's a company that's, well, I was one of the co-founders 12 years ago, in 2000, 13 years ago. Today I'm going to talk about some of the work that we do with them. So that's why it's perhaps relevant to say a few words about SIG, Software Improvement Group. What do? They aim at collecting detailed technical findings about software-intensive systems. So this is written on their website, this is their mission statement. But what they do with those technical findings? They do translate that into actionable information for higher level management. So if we take the tunnel example again, this is about going into the tunnel, looking into the tunnel and seeing what's happening there, collect detailed technical findings, and then report them back to management, and in order to help management deciding what to do next with the problems that people are experiencing when working with the tunnel. So it's looking at, in terms of software, it's looking at software systems, collecting technical findings about it, and turning that into advice about how you can deal with problems related to evolution, related to new versions, performance, etc. So dealing with the technical issues in software systems. And they do that not just in isolation, but together with research from academia, from themselves. So they also fund research, and the work that I'm presenting today is done together with, is funded by them. Okay, so this is the company setting, and this is the big problem that we're working on. So let's turn that into a program for today. What is the big goal that we're working on? Well, the goal essentially is understanding software quality and trying to measure software quality. And so what in software engineering, we're all interested in software quality. We have the ambition of making this beautiful program. But what does it mean to write a good program? How can we determine that a program is good? When you look at it, you often have the intuition, well, this is nice, this is not so nice. Can we turn it into a measurement statement? Like, can we measure that? Well, obviously, it's not possible to have, having just a single measurement saying, yes, this is nice, no, this is not so nice. And so this is a huge challenge, but we can perhaps get a little closer there. We don't know how to do it, but if we don't know something, that means there's an interesting research challenge ahead. So perhaps we can push the knowledge boundaries a little further so that we can get a little further in establishing software quality using metrics. So that's the overall highly ambitious research goal that we are addressing here. When working on that, this means that we're going to propose new metrics and discuss new metrics. Well, when coming up with a new metric, the key question is, of course, how do we know that this metric actually means something? How do we know that this metric is meaningful, that it is practical, that it is useful? So the notion of evaluating metrics is a key when we're going to work on software metrics. So that's the central part of the talk, if you wish. Then, just talking about metrics in general is perhaps not very nice, and it's more interesting to look into a concrete case. So what I'm going to do with you is walk you through a very concrete case about software metrics where we try to measure encapsulation. And I must warn you, that is a bit of research in progress, so it's really something that is under submission, so we may be wrong, and hopefully you have some good feedback that well, can help us get to the next level. So that's about encapsulation, and then what I'll do is I'll take one big step back, reflect on the findings that we have, and try to draw some general conclusions. So this is the program for today. All clear? All clear. Good. Then we need a bit of context. And the context is this software risk assessment. So what's happening there is that we have a system, and this system is it's used by a client, and it's built by a provider, by a supplier. And those two, well, if everything is fine, everything is fine. But this is perhaps not always the case, and sometimes there are issues with systems, and then a third party may come in order to assess the risk. So that is the situation that we're talking about. So there's the software risk assessment consultant who can analyze the system and report that to the client in order to advise him, recommend him what to do. So that's the overall setting. And here is, there are several people involved here. So this is also people intensive, if you wish, although it's not directly about using software, but it's about managing the whole software construction process. Putting this in an architecture context, this is about evaluations. And in architecture we talk a lot about evaluations. We all know the ATEM evaluation method. So I should emphasize that this is about so-called late evaluations. So it's not an early evaluation which you do when you're beginning to build the system, when you just have the requirements and some design. It's about evaluation when the system is already available. So we actually can go into the tunnel and see what's happened in the tunnel. It's not the greenfield situation when we're thinking, what sort of tunnel should we build? It's really the tunnel is already there and we're going to inspect that. So we are late with our evaluation. And another thing we're not looking at is the process. Of course, it's very important how the software process is conducted, and it affects quality in many different ways. However, we're not looking at it today. So important, but just out of scope for this particular talk. Yeah? I talked about quality, and evaluation is about quality. So quality can also mean 1,000 things. So there is luckily an ISO standard talking about quality, and it distinguishes all sorts of characteristics. And today we'll be talking about one particular quality, namely maintainability. So all the other abilities important, but out of scope for today. So we're zooming in and zooming in. So we're talking about maintainability. And what we're actually looking for are metrics to capture maintainability. And, well, you can imagine that several of those metrics already exist. So in that sense, this whole process, this software risk assessment process, can already be supported by metrics. And actually that is also what SRG does. And in the past, lots of assessments have been conducted using all sorts of metrics, but mostly at the code level. So based on this experience with using metrics, we collected some lessons learned from a decade of using metrics in practice. And we wrote them down in a little paper called Getting What You Measure. And before I dive into metrics with you, I think it's important that we understand what the inherent limitations of using metrics are. So that's why I want to walk you through some of these lessons, to 4 of the lessons that we collected in this paper. And the first one is actually sort of reflected in the title of the paper, Getting What You Measure, because if you start measuring things, people start optimizing that measure, well, that may be problematic. So the first pitfall that you should think about is that when you start measuring things, you start creating a tendency to optimize the metric regardless of the root cause. So you start treating the symptoms rather than the real problem. So metric values are symptoms, and it's the root cause that should be addressed. Well, if you don't do this, you're just treating the metric. And this also means that when you're talking about a metric, when you're thinking which metric to include in your metrics program, you are looking for metrics that help you point to this root cause. So just a metric which is, for instance, using information theory or chaos theory to come up with one magical number without pointing you to the problematic parts, that may be not so useful. So we're searching for metrics that make it possible to point to this root cause. So that's one first pitfall, just treating the metric, gaming the metric in order to optimize the value. Another pitfall is that you, well, treat the metric in a bubble. You don't have the context to interpret the metric. So, for instance, you just have a number, but what does the number mean? You have a number, you have a method, and the method has a McCabe index of 5, complexity 5. What does that mean? Is that a problem? Is that not a problem? In order to answer that question, you need to provide context. So we're talking about 2 different contexts. One is my own context, historically. So I am writing methods, I have this particular method, and I know yesterday I had complexity 4, now I have complexity 5. Apparently I made it a little more complex. What should I do about it? Should I increase my test coverage or whatever? That's my own context. But another type of context is not just me, but my peers. If my peers write a method, what average McCabe do they have? Do they typically have McCabe 7? So then I'm a good programmer who writes nice and simple code. Or do they normally have 3? And then I'm a complex programmer who writes a little more complex than what is normally done. So we need to provide this context both in terms of your peers and in terms of your own history. Okay, so otherwise you're measuring without the context. So that's, I'll later tell a bit more about how to do this and how to build up a benchmark in order to take care of this. Third pitfall, just having so many metrics that you're measuring everything. If you can measure it, it doesn't mean that you should measure it. And especially if you want to report to management, what's important is just to have important facts, and measuring everything is not going to be helpful. Having said that, if you just have too few metrics or just one, if you have a one-track metric, that's also not going to work. And we all know that design is about trade-offs, and we can optimize one thing, but we cannot optimize everything. So if one goes up, the other probably goes down. So we have to carefully craft our metric suite so that the negative side effects of one metric are captured by another. So composing your metric suite is something where you have to carefully think about, well, the design space that you're working with and try to capture that in your metric suite. So those were 4 4 pitfalls that in the experience of actually using metrics in practice often came around. So when working with metrics, you have to be aware of this, and only then you can make some progress with metrics. Concerning this second pitfall about putting metrics in context, there's a nice paper by Thiago Alves and others about how this is done. So what you need is a benchmark, and at SIG this is a large benchmark covering hundreds of millions of lines of code of industrial systems with their metric values, and that is used to provide the context of the peers. So that's how it's done. And then based on that, thresholds are being determined, like 90% of the people who are writing methods have a McCabe index less than 15. You are having more than 15, you are at risk. Your system is beyond what normally is happening. So that's a very simple approach, effective, which works well. Some tricks you have to take care of, and the most important one is that all these metric values, they're typically not normally distributed. It's usually a power law, so you have to take care of that when doing the statistics. But once you do that, things are relatively simple. So you put the metrics in context by having such a benchmark. And in this case, we're talking about an industrial benchmark, but this could also have been, of course, an open source benchmark with everything on GitHub or wherever. So you could do this in many different ways. So that's putting the metrics in context. And this was based on reflecting on some of the experience. So in 2009, when there was 5 years of experience, we also did a little reflection. And there we looked at 50 assessments that had been conducted for a while. And all those assessments, they were really about code level metrics. The assessments also, of course, included architecture constraints. But for those, well, we just didn't know which metrics to use, so no metrics were used. Instead, there was a sort of a checklist that you would walk through and in that way deal with the architecture constraints. But we all know that, well, architectures allow or preclude nearly all of a system's attributes, as Clemens put it. And so architectures are important for quality, so we cannot ignore it. So what we then decided to do was, well, after our 50 assessments in which architecture plays a role, let's look at what people actually did. So how did the assessors actually use architecture in these assessments? So we decided to do a little qualitative study on how people were actually using this. So that's what we did, and around that time there was a sort of suggestion that in any assessment you would talk about high-level design, about modularization, and about separation of concerns, which are the 3 issues listed here. And what we did, we looked at how these issues were discussed in the reports, and we came up with a number of words that commonly occurred, which indicated how the assessors dealt with architectural issues in those reports. And one of the other outcomes was of this study was, well, in order to make the discussion about architecture a little more objective, a little more fact-based, what we would really like is some architectural metrics here in place. So that's, well, this was a challenge, and Erik Bouwers, the PhD student, had done this, and then he decided, okay, that's a challenge I want to pick up, so we started working on it. And so that got us into architectural metrics in a way. All clear? All clear. So, architectural metrics for the purpose of maintainability. And maintainability in ISO terms is defined as the degree of effectiveness and efficiency in which a product or system can be modified. So it's all about change. And this same standard divides these characteristics into a number of sub-characteristics. Things that you have to deal with when thinking about ease of changing stuff. And the 5 characteristics are listed here. And what we're going to do today is really zoom in on one of them. So the metrics suite, of course, must cover all of them. But today we're zooming in on one of them because you cannot have metrics for everything. And we're going to work on modularity. And for modularity, ISO also has a definition. The degree to which a system or computer program is composed of different discrete components, such that a change to one component has minimal impact on the other. So it's really about localizing change. So I can change one part and the other parts don't care. It's really, change is isolated. It's nice in one place. And so if you look at the ISS here, if I change one solar panel, the other ones will still continue to work. It's modular. So that's a nice property to have. And then the question, of course, that's natural that we started asking, how would you measure modularity? Can you measure modularity? So if any one of you has a proposal, please come to me afterwards and perhaps we can work on it. So this was the ISO definition of modularity. Is this a strange thing to want? No, of course not. In fact, Kent Beck, which we all know from explain programming and test first design, he wrote a blog post last year, and actually it was about the same thing, phrased a little differently, but he said things that change at the same rate belong together. And so if things are changing frequently, often you want to hide it behind an interface, and the interface should not change often. So things that change quickly should be insulated from things that change slowly, and this is information hiding. The implementation may change, but the interface will remain the same. So we all want this isolation of change. That's a good thing to want. So, yeah, that's then the challenge that we picked up, and we thought, let's think about how to measure this. So the question that we are seeking to answer is, can we find software architecture metrics that can serve as indicators for the success of encapsulation of an implemented software architecture? Yeah? So can we take an existing system and just do a magic measurement, and then we know 0.5 modularity, and we have the context and we have the history, so we actually know that we are more modular than our peers and we're doing good. Or we are less modular than our peers and we have some challenges to face. This is the big challenge that we're working on. Still in progress, the paper is in submission, and we're still really rethinking what we're doing, so feedback will be very much appreciated. So this is the plan. Working on searching for this type of metrics. But when searching for a metric, well, not any metric will do. And we are looking for metrics that meet certain criteria. So in this case, we came up with a number of criteria in an assessment context for such a metric. And the first one is obvious. It should be a measurement that is actually aiming at measuring encapsulation. So that's logic, because that's our target. What we also want is that this metric is defined at, or can be lifted to, the system level. So we're looking at architectural level encapsulation. So not just in one class, but we wanted to see of the full architecture what is going on, the full system. Another constraint that we put is it should be relatively easy to compute and implement this metric. This is not because we're lazy. If it can be implemented, we are happy, but there should be no manual effort, or there should be no subjective component. So an example is if the metric needs an assignment, a mapping, a traceability relation between, say, features and architectural components. That is nice if it's there. In practice, it is almost never there. So if then you would want to do it, you would have to create this mapping first. So this is a nice assumption that this mapping exists, but it's just not doable in our own setting. So we exclude those things. The metric should be relatively easy to implement. Fourth requirement is that we want to use it for many different technologies. So whether it's COBOL, Java, C#, Pascal, C, we want a single concept that is usable across different technologies. Perhaps you cannot compare the values, but at least you have the same type of metric. So that's a goal we have. The fifth one we already covered. We don't want to support gaming the metric, so we should have a metric that allows for root cause analysis and gives us some clues on what we should do about all this. And the sixth one is a challenge in any metric. Metrics are always, the dominant metric, whatever you do, is size. And size is always going up, mostly. And thus, metrics that are strongly correlated with size, well, then you might as well measure size. So if it's correlated with size, well, we have a metric for that called lines of code. So we're looking for other metrics that are not correlated with size, and not influenced by the volume of the system under evaluation. So this is the 6 criteria. And those are the constraints under which we're searching for metrics. To make number 2 a little more concrete, and also related to number 3, this actually relates to the question, what do we mean by an architecture? And we take a rather limited view on architecture in this work. So we say an architecture consists of a system, which consists of components, which consists of modules, which consists of units. So it's really simple hierarchy system, top level components, direct modules, and the modules can contain units. In terms of Java, system contains packages, contains classes, contains methods. That's the simple view, but this simple view you can impose on many different technologies. And then between those you can have relationships. And dependencies. And these dependencies can have a cardinality and some properties. Moreover, an important thing, the architectural elements themselves can have some sort of size associated with it. So we know the size of units, and we can aggregate it to sizes of modules, and then sizes of components and sizes of systems. Not that this size is directly the measure, but this size can be part of putting the other graph properties of the dependencies into perspective. And so we know what the component decomposition is, and we know what the sizes are. That's all we are willing to, well, that's all we need to know about, to talk about architecture. It's a particular view on architecture, but it is a representation of the system under analysis. To make it, to illustrate it, here is a bunch of modules, different names, and larger circle means larger modules, smaller modules. And what we're going to do is group them into components. And those components, well, there can be dependencies between the modules, and the modules dependencies can be lifted to the system level. So this is actually all we are assuming, and well, the question is, can we do meaningful things with just this level? Okay? So, well, when thinking about metrics for the encapsulation, the first thing you do, of course, is try to stand on the shoulders of giants. So we were searching the literature and identified well, over 14 metrics that could in principle be used. So we hold them against the criteria that we formulated, and in the end we ended up with 11 that really kind of met all the criteria which could be defined in our architecture model, which have root cause analysis, etc. And so those were the constraints we used and some of the metrics that came up after an analysis of the literature. I should say, however, that one of those metrics, or actually some of them, came from our own research. So those are part of the metrics suite that we're going to assess. And our own analysis was based on a metric that we call dependency profiles. And it's really about components and dependencies between those components. So here we see one of those components. And in the component there can be different modules. In a component there can be several modules. But we can divide the modules in a couple of categories. So we can have modules which are only collaborating internally within the component. So there can be internal modules which really only focus on internal activity. We can also have certain modules which are invoked by the outside world, so the provided interface, if you want. And we can, of course, have modules which interact with the outside world, which use the outside world, the required interface, if you want. And there can be certain modules which are transfer code, which are coming from, which have both incoming and outgoing edges to other components. So this is those are four groups of modules that are of interest. So now let's try and see if we can turn them into perhaps metrics or so. So what we're going to do is look at the relative size of those different module types. So we can come up with a quadruple, a four tuple, where we look at the percentage of internal code, the percentage of inbound code, the percentage of outbound code, and the percentage of transfer code. For instance, we can have a system where there's 40% internal, 30% incoming, 20% outgoing, and 10% transfer code. Or we can have a system which is a bit differently organized, where 60% is internal code and a lot less is outbound and inbound code. And those are different types of systems. And well, perhaps intuitively you could say, well, the more internal code we have, just statistically speaking, the more local the changes may be. Would that make sense? Well, it makes sense to me. So perhaps this could be, these dependency profiles, and in particular the internal code base, could be a meaningful way of dealing with a locality of change. Hypothesis, worth investigating, and comparing to some other metrics. So that was the plan. Before doing that, we took a little look at these profiles themselves. So here you can see a benchmark of like 100 systems where we looked at the profiles. So here you see systems where there's very little internal code. So this is all the systems where there's internal code. The gray, dark gray is the provided interface. So what you see is that the provided interface is usually nice and small, actual interface classes. Then there is this bit, which is the outgoing code, which is outgoing dependencies. And that is actually quite large. So people apparently take good care of their required interface and take less care about their take good care about their provided interface, and they explicitly manage their own provided interface, but are less careful when dealing with the required interface, the systems they depend on. And there is some transfer code which is usually a bit smaller. So this gives an idea of how these dependency profiles occur in different systems, different technologies, and that they indeed vary, and that perhaps you can say something about it. Yes?
What are these 100 systems?
So each line is a system.
Okay.
So the bottom line is a system where there's a little internal and little transfer, but a lot of incoming code.
Yeah, so what 100 systems? Like, is there like a database of these systems that everyone can access?
No, these are, it's in the paper. So the paper is this one.
Oh, okay.
And it's a mixed, it's partly open source and it's partly their own commercial collection. But it's described in this ICSM Arrow paper from 2011. So there are the details of the benchmark. But partly is closed, so but part is open and you can read it. So this was our own contribution to the encapsulation metrics. The other metrics that we looked at, that we include in our experiment are these ones. One from Lionel Briand, a couple of by Lacos, who wrote a book about C++ implementation, and 3 of the categories from our own dependency profiles. So those were metrics that we partly took from the literature and partly invented ourselves. And we wanted to know, well, which one, how do these perform in order to measure encapsulation? But then the question, of course, is how do we evaluate that these metrics properly define encapsulation? Tricky question. So we came up with 2 different answers and 2 different evaluation approaches. And the first one is a quantitative approach, where we really look at statistics, and we're going to look back in history of a couple of systems and see whether there in those old systems, in their history, whether there was local changes in one component, and we can see that in the version management system, and we can see the values of our metrics, and then we can try to correlate them. So that's the plan there. And that's sort of the construct validity. Do these metrics actually, are they related to encapsulation? So that's one evaluation that we're doing. That's this one. The other one is, well, assuming that they actually work and actually do some good stuff with encapsulation, are they of any use? Can the assessors actually work with them? Does it make the life of the assessor better? So is the selected metric useful in a late architecture evaluation context? Because that is the real question that matters. And the first one is nice, and we can demonstrate some statistical properties, but this would be the real success. So let's see. So we're going to try this, and we start with the quantitative approach. So the first question, of course, is how do we compare, here I want to be, how do we going to do the comparison to locality of change? So there we are going to look at the change sets in a repository mining setting, whether things are changed together. So let's look at that a bit, let's look at this notion of change sets. So here is again our system, and each commit in the repository results in a sort of a change set. So here, for instance, we have a change set where in component C1 2 modules are changed, and in component C3 another one is changed. So the whole change set is A, C, Z, and it affects 2 different components. That's one commit. Commit later, this happens, and B, D, and E are changed together, but no other components. So this is a nice local change, so we like this one. And the previous one was not so local. Here we have another change, all in component C2, and again a nice local change of Q, R, and U. And the final change set where again 2 different components are changed. So we can distinguish between local change and non-local change by looking back at the history. And so our observation is local changes sets are good. And what we then can do, if we have local change sets, we can combine them into a series of changes and then say, well, the more local changes in a series, the better the encapsulation worked out. And so we can say, we combine them into series and the percentage of local change is what we're going to look at. Yes?
So you remarked earlier on gaming the metrics. So can't I game the metrics by simply creating one giant component that includes everything?
Yeah, so this is not about, so this is the experiment in order to evaluate the metric itself.
Okay.
And so we're looking back at the history.
Right.
And indeed, if you have the full history available, then you can always look at the local change. So that's useful information anyway. But now we're looking at, can we use the history to say whether a snapshot-based metric can actually predict some of the future locality of change. So this is the good observation. We're happy with this. But there is a bit of a downside and a trick that is involved here. Because when I make a change, well, the metrics can change too. A change may affect the value of the metric. I can make a module bigger. I can add a dependency. I can remove a module. So, and some of the metrics may depend on that. So what we need to do, and actually, we came across this issue in our research, and then we thought, well, there must have been many repository mining papers facing the same problem. And then it turned out that often this problem is ignored in research. So I had a discussion with you indeed, and I immediately asked this question, and you were dealing with it correctly. But quite a few bug prediction papers ignore this issue, and well, I think that will certainly affect the results. Let's put it like that. So what we're going to do to address this is we're going to take these large change sets and change them, cut them off in a series of sequence of stable change set series. So we're going to make them stable, and then within those stable sets we can do our meaningful correlation. And so to illustrate this, so here we have our components again, and we have a change set with makes some modules bigger and others smaller, and add some dependence. So this can happen, and we have to deal with that. So our solution is indeed stable period identification. So here we have a number of snapshots, and here's our metric, and initially it's 3 for a number of consecutive snapshots, but then something happens and it bumps to 4. So we're going to treat this as one period and this as another simple period, and within those periods we're going to do our assessment. That's the, yes?
So you're kind of redrawing the kind of commit boundaries so that it's like...
Yeah, well, not the commit boundaries, because we don't turn them into single, we don't turn them into a large commit. What we're going to do is we take a number, each commit indicates whether 2 different components are or not are touched, but there is a series of commits, and those commits, as long as they don't change the metric values, we turn them into one stable period. And then we look at, in that stable period, what percentage of commits were local. That's what we do. So, yes?
So were you able to find long periods of stability?
That's a good question. I think I have the slides with the tables in the backup slides. But let me first give the experimental setup, and then I'll try to answer the question. So we took 10 open source systems, which had a long history of sometimes 10 years. And what we did was determine the metrics on a monthly snapshot. So every first of the month we took a snapshot and computed all the metrics, and then based on those we started determining the stable periods. And then per metric indeed determine the stable periods, and those periods change per metric. So every metric has its own stable period sequence. Based on that we did the Spearman correlations, and in order to find correlations that are moderate or even strong. That's what we hope. Assess the significance, of course. Assess project impact. I'm not going to talk about it. We did some statistical tricks to eliminate the chance that one project was dominating all the results. So we did some backward elimination there. and then we interpret the results. To answer your question about how long the stable periods were, several months, this could certainly be. So in that sense, and it's not so strange because the metrics aim at capturing architectural level information, which you hope you would not change too often. So in that sense, longer stable periods are logical.
Are the stable periods correlated in any way, either positively or negatively, with the degree of change? For example, we could imagine a period of a few months in which there's just a feverish amount of activity in the repository and they're trying to meet a deadline. And then after that, the rate of change slows considerably.
We did not look at that, but that is imaginable. Certainly, if there's little activity, it will be very long stable periods. And if there's lots of activity, then within the 1 month, things will have changed. So it will be very short stable periods.
Well, not necessarily, because we can imagine a period of a system that's extremely well encapsulated, in which there's a high amount of activity, but nonetheless,
that would be very interesting to
see a
investigate.
stable period.
Yes. Interesting future research question. Yes, nice.
Or injection of financing.
Yes.
Sorry?
As financing comes in, there's a big ramp up. As financing comes in, there's a big ramp up in activity.
As financing comes in, yeah, we haven't. These are open source systems, so I'm not sure how that would differ.
So you didn't look at any tying to the system's actually what it's trying to accomplish has changed significantly. You're not looking at the somehow feature tracking, especially with the open source systems.
No, we did no. So we really only looked at the. But I agree that it would be interesting to look at. So these are the systems, and it would be interesting to take the stable periods into account and then manually inspect what was happening in those periods for a selection of. That would be interesting. Yeah, I'm not sure. I can show the slide with the stable periods, but I won't. It's in the paper that was listed. So here are some of the systems. I gratefully acknowledge everyone who worked on AgriUML here, because that was one of the systems that we are investigating. Thank you. So they vary in size and age. Some of them are over 10 years old, some of them are a bit younger. Initially, some of them very small, a couple of thousand lines. In the end, some 100,000 lines, so vary.
Okay, but you were arguing before you wanted scale independence. You wanted to be scale free. Okay, but by many standards, these systems are microscopic.
Yes. So the question is, so here we wanted to do so SIG knows all about the sizes, and there are many bigger systems that they are analyzing. So here we want we are looking for systems that are open source, which has a reasonably long history, which are available. So it wasn't easy to find. Yeah. So we could have done this, of course, even for those large systems having 10 years of history. Not all systems have that so easily available. And actually doing this is also quite a bit of effort. So while I agree that it would be nice to repeat this for many different large systems, that is also quite a bit of effort. So we were thinking initially, let's do it with this. If the results are positive, we inspire you to repeat the experiment on your own bigger systems. So that's the plan. Okay? Yeah, and then actually I told you the whole plan. It's just executing the plan, because the clever steps I already discussed. So then all we want to know is the results, right? There we are. So here are again the 11 metrics. Many of them have not very strong correlations, but 3 of them have.
These correlations with size, or?
No. These are the correlations between the percentage of local change and the actual metrics themselves in those stable periods. So those were the ones we were looking at. And if you look at the bold ones, those have correlations which are moderate. Yeah, which are moderate, and they are below 0.3 and 0.5, and by most statistical standards, that's a moderately strong correlation. Above 0.5 would have been better. And the good news is that the p-values are less than 0.1, which is 0.01, which is something we like. So we trust the statistical significance of what we found here. So that's good. The corrected p-value is the Bonferroni correction for those who are interested in the statistics, because we're doing multiple experiments, all with a 1% chance you may run into well, good results by accident, so you have to divide them a bit. So the winners are those three in a way, given the 0.1 and the correlation, and those three actually come from this one, and actually corresponds to the percentage of internal change. So the percentage of internal change of those 11 metrics in those 10 open source systems turns out to be the best predictor of locality of change. So that's something where we were quite happy about. And you have a question? Or not?
Now I'm trying to understand what that means. Can I interpret that to mean that the developers were very careful about the interfaces they imported and the interfaces they exported?
I'm not so sure that that is the interpretation. So if you, it depends on where you put the focus. If you put the focus on internal, then yeah, what they cared about was keeping as much code as possible local to the particular package. Yeah, and that indeed corresponds to making sure that your interfaces are small. So yeah, in a way, yes. Yeah. Okay. Any other questions at this moment? Of course, any experiments, including this, and so we are happy with this result. So we were proud when we were seeing this, and we thought, cool result. But in any result that is cool, there are also, of course, all those threats to validity. And you have to carefully analyze them. So that's also what we did. And there are actually a few things that you should, well, take into account when looking at this. And one of them is, we presented this as a metric for encapsulation, and we equated encapsulation with percentage of local